So now we're just about ready to wrap things up. We proved in the last video that if P and Q are two different continuous maps from mod K to mod L, but they're homotopic to each other, then they have the same effect in homology. The maps P star and Q star from the homology of K to the homology of L are the same. So we can reformulate that slightly in language of category theory as follows. We can make a new category, curly C. The objects of the category are simplicial complexes, and the morphisms from K to L are just the homotopy classes of maps from mod K to mod L. So remember what this notation here means. We look at continuous maps from mod K to mod L, and then we want to impose an equivalence relation where we think of two maps as being equivalent if there's a homotopy between them. The equivalence classes are called homotopy classes. And this set with the square brackets, that's the set of homotopy classes of maps from mod K to mod L. And because if two maps are equivalent, if they're homotopic, then they give the same effect in homology. So that means we can regard HN as being a functor from this category curly C to the category of abelian groups. And another kind of consequence, same circle of ideas, that if P is a homotopy equivalence, then P lower star is going to be an isomorphism from H star K to H star L. So we could actually deduce that from the categorical point of view, or we can just spell it out as we'll do here. And so if we've got for P to be a homotopy equivalence, that means by definition that there's a map Q in the opposite direction that's a homotopy inverse. So Q is a continuous map from mod L to mod K with the property that Q composed with P is homotopic to the identity map from K to itself, and similarly P composed with Q is homotopic to the identity map from L to itself. So by this homotopy invariance fact that we wrote up here, because P composed with Q is homotopic to the identity, that means P composed with Q lower star is equal to the identity star. And similarly, Q composed with P lower star is the identity star from H star L to H star L. But also, homology is functorial, so that means that P composed with Q star is P star composed with Q star, and id star is the identity. So here we can say this relation here is the same as saying P star composed with Q star is the identity, and this one here is the same as saying that Q star composed with P star is the identity. So these two relations here are saying that P star and Q star are inverses to each other, and so they're both isomorphisms. So as an example of that, let's let K be any abstract simplicial complex such that the realization of K is homotopy equivalent to Sn minus 1. So it's actually not very hard to produce lots of complexes like that. I mean, so for example, if we're looking at n equals 3, so the two-sphere, the ordinary sphere, the octahedron is a simplicial complex that's homeomorphic to S2. The icosahedron is another simplicial complex that's homeomorphic to S2. So K could be either of those things. Yeah. But yeah, so if the realization of K is homotopy equivalent to Sn minus 1, well, that's also the same as the realization of the abstract boundary of abstract delta n, so that means that by this corollary here, the homology of K is isomorphic to the homology of the boundary of delta n. And we calculated that homology of the boundary of delta n before. You get a Z in HIK if I is 0 or I is n minus 1, and 0 in all other cases. So that tells us the homology of any abstract simplicial complex whose realization is a sphere. So now we can revisit various applications that we discussed earlier. Okay, so for example, let's suppose that n and m are different, natural numbers that are different. So homology of Sn and homology of Sm are then going to be different because we know what those are. There's a slight special case for n where m being equal to 0. There you get a z squared in degree 0, but otherwise the unique dimension in which Sn has homology is unique dimensions are 0 and n. And from that you see that H star Sn and H star Sm are different when n and m are different. And because they have different homology, that proves that they're not homotopy equivalent. And if they're not homotopy equivalent, that means they're not homeomorphic. So remember which way around it goes. Homeomorphic implies homotopy equivalent, and therefore not homotopy equivalent implies not homeomorphic. So again, so that's geometrically it feels reasonably obvious, at least where n and m are so less than 3, and we can visualize these things. It seems fairly clear that Sn and Sm are not homotopy equivalent. Now we finally managed to give a formal proof of that. As a deduction from that, if you take Rn and remove one single point, then that's homeomorphic to Sn minus 1 crossed with R, and homotopy equivalent to Sn minus 1. And so if Rn less point and Rm less point, the only way they can be homotopy equivalent is if Sn minus 1 and Sm minus 1 are homotopy equivalent, and that can only happen if n equals m. And now it follows from that that Rn and Rm are not homeomorphic if n and m are different. The logic goes as follows. I mean, if Rn and Rm were homeomorphic, you take a homeomorphism, then you remove one point from Rn, and then you remove the image of that point from Rm, then you get two spaces that again would be homeomorphic. Rn with one point removed and Rm with a different point removed. And if they're homeomorphic, then they would be homotopy equivalent. And it would then follow that Sn minus 1 and Sm minus 1 would be homotopy equivalent, and therefore n and m would have to be the same. Okay, so we mentioned this before as theorem 13.1, but we weren't able to give a complete proof because we didn't have homology groups. And now that we do, we can finish that off. Another thing in the same line of argument, we've seen that the homology of Sn minus 1 is different from the homology of a point, because homology of Sn minus 1 has two z's and the homology of a point has only one z. And so from that it follows that Sn minus 1 is not contractible. And we proved earlier that any retract of a contractible space is again contractible. So Sn minus 1 can't be a retract of the ball Bn. And that lets us complete the proof of the Brouwer fixed point theorem. So we sketched this out before, so let's just remind ourselves how that goes. Okay, we want to prove that if you've got a continuous map, f from Bn to Bn, then it has to have a fixed point. If it doesn't have a fixed point, then we do this this trick. We start the point fx, and we draw a line from there to x, and that's kind of a well-defined thing to do because fx and x are different. So we can there's a unique line starting from fx, passing through x, and then that will hit Sn minus 1, and the point where it hits Sn minus 1 we define to be Rx. Okay, and we spelled out the details of this a while ago. That this construction gives us this map R is a continuous retraction from the ball Bn onto Sn minus 1. But as we mentioned before, that's not possible, because if Sn minus 1 was a retract of Bn, then it would be contractible, and so it would have the same homology as a point, which it doesn't. So we've arrived at a contradiction. There must have been a fixed point. And also we calculated the homology of a bunch of different spaces using the Meyer-Vectoris sequence in an earlier section. In all of those, we repeatedly used the idea that homology would be homotopy invariant, so that we could just see the homology groups of various auxiliary spaces that came up along the way. And now that we've proved the homology is homotopy invariant, we can go back and make all those arguments more rigorous. And that is where we'll finish the course. I hope you've all found it enjoyable.